and solve all of it. So, so the first 5 problems was list the oxidation numbers of the underlying element / ion in the blank. We know all but 3 are compounds, so they're going to the sum of oxidation numbers is going to equal the charge of 0. For number 3, it's going to equal the charge of -2. So there are 2 sodium. We're going to add to it 2 sulfur and add 3 oxygen, and that's going to equal 0. We know sodium is group 1. Group 1 always has +1. And we're trying to solve for sulfur. And we know oxygen always has -2. So that would be 2 plus 2s minus 6 is equal to 0. 2s equals 6, moving it to the other side. Subtracting 2 from both sides, we get 2s is equal to 4. And dividing by 2, we see s is equal to 2. So that means +2. Copper plus oxygen has to equal 0. We know oxygen is -2 always. Thus, whenever we move this over, that would be copper is equal to 2. So copper is +2. Number 3, carbon plus 3 oxygen has to equal the charge of -2. We know oxygen is always -2. So that'd be carbon minus 6 has to equal -2. Add 6 to both sides. We see copper. -2 plus 6 is +4. So we get a +4 there. Last one, we have potassium plus chlorine and plus 3 oxygen has to equal 0. We know potassium is always +1. 3 times -2. So that would be 1 plus chlorine minus 6 has to equal 0. Moving this over here, that would be 6 on that side. And subtracting 1 from both sides, chlorine is equal to 5. Or rule is if it's only a single element by itself. What is it? 0. So oxidation number should have been fairly straightforward. Just solve algebraically for the missing term. Oxygen's always -2. Hydrogen's always +1. Group 1 and group 2 is equal to their group number. All of these only require those rules. The sum of them adds to whatever the charge is. Element by itself is always 0. So when an element's oxidation number decreases, well, when it decreases, it means reduces. Another word for decreases is reduces. From +1 to 0, what is it? Well, it's reduction. If you remember oil rig, reduction is gaining electrons. Reduction is gain. Oxidation is loss. So this should have been gain. So figure out the oxidation numbers for all the elements. This is just like 1 through 5. If it's by itself, it's what? 0. Hydrogen is always +1. Since this is neutral, we have a +1. That means chlorine must be -1. +1 minus 1 add together to give you 0. Ignore the coefficients. Magnesium is in what group? 2. So that means everything in group 2 has a +2. There are 2 chlorines. What must their oxidation number be to counteract the +2? -1. H2 must be 0. So we see on the left-hand side, magnesium 0 is going to magnesium to +2. It's being increased. So it's being oxidized. So magnesium is the element or ion being oxidized. Chlorine on the left is going from -1 to -1. This is what we call a spectator ion. If it doesn't change, it's a spectator. And we see hydrogen on the left is going from +1 to 0. It's being reduced. So hydrogen must be the element being reduced. We're seeing this break apart. So we're seeing it break apart into 2 things. We're seeing it lose electrons. Oxidation is loss. We're adding electrons on the left-hand side. So that's gaining electrons to form this. It's going from Mn4 plus to 3 plus. So that's reduction. And likewise, this one's also reduction. It's gaining electrons. So this one, I'm taking 2 elements, combining them together to make a compound. It's the definition of synthesis. Whenever you take 2 things and stick them together to make one thing. So we have an AB making A plus B making AB. So here I'm replacing Zn with H. So that would be single replacement. I'm starting with one thing and splitting it off into 2 things. So that would be decomposition. I'm reacting something with oxygen. Combustion. I'm swapping Ba with Ag. And swapping Cl and NO3. Kinda. I'm not doing it at the same time, but there's basically I'm getting this, I'm moving this over here and this over here. This is double replacement regardless. I think everyone for the most part did good on this. This one will react. It looks like most of everyone just guessed. So remember activity series. If magnesium is more active than aluminum, it will steal the chlorine. So which is more active, magnesium or aluminum? So it's whichever one's higher, whichever one's more active. So if I go down and see magnesium is indeed more active than aluminum. It's above it. So magnesium will come in here and steal it, and we end up with aluminum plus magnesium chloride. So that will react. Iron. Will iron steal chlorine, or will copper stay attached to chlorine? Which one is more active, iron or copper? Coming over here, going down. I see iron first and copper down here, so iron is more reactive, or more active, so iron will come over here and steal it. So this will react. Which is more active, lithium or sodium? Lithium is the most active metal on the periodic table. Lithium will most definitely steal it and replace it. So this will become Na plus lithium chloride. So if you put lithium and sodium in the same location with chlorine, lithium will win out. That will react. Silver versus iron. So silver is right here. and iron is right here. Iron is more active. Iron will always stay attached to oxygen. Silver cannot replace it. So this will be not react. So iron is more reactive with oxygen than silver is. Everyone did good on the balancing. So we have 1 chlorine here, 2 chlorine there. So we need to double up on the right-hand side. That gives us 2 sodium and 1 sodium here, so we need to double this up. Now we have 2 bromine, so that's good. Yes?
Rotary by the end of it. Yes, the rotary club needs to be turned in today. It should be turned in Friday, but today will work.
This one, so 2 phosphorus here, 1 phosphorus here. We need to double this. So we have 6 oxygen on the left, 4 on the right, or 8 on the right. So we can do 5. We need 3 more oxygen, so you can do this. We see 6 hydrogen. Now we have 6 hydrogen. Everything's balanced. So 3 oxygen here, 2 oxygen there. We can do 3 and 2. Now we need to double the potassium and chlorine on this side, balanced. Let's see. So this one's more involved. So we have on the left-hand side 1 hydrogen. And we have 2 hydrogen over here. So we can temporarily increase this to 2, giving us 2 hydrogen there to balance it out. On aluminum, we have 1 and 1. And on chlorine, we have now 2. And over here, we have 3. So to get chlorine now to do, we're going to multiply this by 3. That gives me 6 right there. And multiply this one by 2. So that means I now have 6 hydrogen and 6 chlorine. Over here, I now have 2 aluminum and 6. So now I need to double aluminum here. And I need to triple my hydrogen over here to get that 6. Now they all balance. So the correct answer is 2, 6, 2, 3. So 3 hydrogen, 2 hydrogen. It's a 3, 2 case. And I don't think anyone ever got this one right, even with corrections. So, indicate whether or not everyone is aqueous, solid, liquid, or gaseous. I don't know why anyone was guessing gaseous and liquid unless you knew it. I said, your test is going to be whether or not it's aqueous or solid. Unless you know it's like something like H2O or CO2 for gas. So everything is either going to be aqueous or solid unless it's something you already know is liquid or solid. Or liquid or gas, I mean. Almost everything in the world is a solid at room temperature. Unless it's dissolved in water. Even then, it's still a solid dissolved in it. So, Na2CO3. Is this aqueous or is it not aqueous? So, if it's over here, it's soluble, and that would mean it's aqueous. If it's an exception, that would usually mean it's a solid. If it's over here, it's a solid, unless it meets an exception, which would make it aqueous. So, CO3. CO3 is right here, doesn't meet any of the exceptions. Sodium, that's an alkali metal. Alkali metal means it's soluble, so it would be aqueous. Chlorine. Chlorine is soluble unless it's mixed with silver, lead, or mercury. That is calcium. So that means it's over here, soluble. So that means aqueous. CO3. CO3 is insoluble unless it's mixed with an alkali metal. Is calcium alkali metal? It's an alkaline earth metal. It's group 2. Alkali metal is only group 1. That means it's not soluble. It doesn't meet any of the exceptions. It's right here. Not soluble or insoluble. And that means solid. You should know that salt is soluble. But looking at these rules, chlorine is soluble unless lead, mercury, or silver. Na is neither of those, so that means it's soluble. Ag. So, in all of these, they're all Ag except for one of them. Iron sulfide. So we have a sulfide right over here. If mixed with iron, I do not see iron anywhere in the exceptions, so it's right here in the insoluble. So, solid. HCl. I said if it's an acid, put aqueous. All acids that we'll deal with, aqueous. H2S is a gas. I've already filled that in because that's something y'all wouldn't know. H2S is not a common chemical that y'all have encountered, so I already went in and filled it in with gas. FeCl2. So chlorine. It doesn't. Iron is not one of the exceptions, so it is soluble. So AQ. Bromine. Bromine right here. It's mixed with iron, not an exception. So that means it's over here. Soluble, so that's aqueous. Phosphate. Phosphate's right here. Potassium is an alkali metal. So that means it meets one of the exceptions. So that means it's soluble. Everyone see that? It is PO4 is mixed with K. So that's an alkali metal. So it's normally insoluble unless it's with an alkali metal, which makes it soluble. PO4, again, is insoluble unless with an alkali metal. Fe is not alkali metal, so that would make it solid, not soluble. Bromines are soluble unless mixed with one of these. That's not one of them. So it would be aqueous. It will dissolve. Bromines dissolve unless it's one of these 3 chemicals. Magnesium. Magnesium is not a compound. You should know that it exists as a solid. That's a standard one. It's not anything particular. Sulfate. SO4 is right here. Copper is not one of the exceptions. That means it's aqueous. Sulfate again. Not one of the exceptions, so aqueous. And copper is a metal that's solid. So, on all of these, aqueous and solid, it's mostly always aqueous. And with one or usually there's only one solid on it on the right hand side. But mostly it's all aqueous and solids you've been putting. Aqueous is the number one thing. This one right here. So how you do an ionic equation is you break it up into ions. So this is one ion. This is another ion. This would form Mg2+. That would be OH negative. So breaking up these all into their ions. Mg2 plus NO3 negative. And water is not ion on it. It doesn't dissolve. It's not aqueous. So we keep it as liquid. So everything that is aqueous is broken up into ions. That's the definition of aqueous. To dissolve into ions when placed in water. Water does not break into ions when placed in water, so it stays a liquid. If it appears on both sides of the equation, cross it out. What's left, we rewrite down. So H plus makes water. And this is the ionic equation. It's balanced. So that's it. I don't think anyone attempted the bonus. What type of reaction is this? We have one thing on the left, and that's it. So what? No, we have one thing on the left. It's not reacting with anything. Decomposition. If you have nothing else, if you're not reacting anything with it, if you're not adding anything to it, the only possible answer is decomposition. What is it going to decompose to? So let's list some common things we can do. What are some common things we can make out of that chemical? Common compounds. We can't have ions. What's a compound that we can make out of that? CO2. What else? So we have nitrogen, hydrogen, carbon, and oxygen. Ammonia. NH3. What else? Hydrogen and oxygen can make water. So looking at all the possible ways this can decompose, I mean, technically you might argue that you can make some O2, some H2, some carbon, and maybe some N2. But looking at the ions, so we have NH4 plus, and we have CO3, 2 negative. What can we do to this one to get one of these? What's the most simplest thing we can do? We can remove an H plus from it. So we can remove an H plus, leaving us with this one, NH3. What's the simplest thing we can do to this? we can remove an O2 negative, making it CO2. And what do we have left over? H plus and O2 negative. They react to form water. Now we just need to balance this. So this chemical here is aqueous. So anything with ammonia is aqueous. There is no exceptions. We have 1, 2, 3 oxygen on the right, 3 oxygen on the left, 1 carbon, 1 carbon. We have 8 hydrogen on the left and 5 hydrogen on the right. We have 2 nitrogen and 1 nitrogen, so let's double that. Now we have 2 nitrogen, 6 plus 2 is 8, 8. So there we go. All balanced up. That's how ammonia carbonate decomposes. Again, this is, I told you this was somewhat difficult, as you have to think about the ions. How are they going to become stable? The most easiest way for this one to become stable is by losing an H plus ion from it, turning this into NH3. This is going to become stable. Again, it could lose a carbon and an oxygen, but that's really complicated. The most easiest thing is for this to just lose an O2 negative ion, meaning that this is going to convert it into CO2. The remaining 2 ions can react together to make H2O, which we saw from this formula here. Well, we did it with OH. This one will still, if we have H plus O2 negative, they do make water if we double the hydrogen. Hello? No, he's been absent all day. Mm-hmm. Alright. I want to go over molarity. Let's say we have 100% vinegar. Does anyone know what 100% vinegar is called? It's a term. It's a weird term. I don't know why it's called this, but it's called this. Glacial. I have no clue why glacial comes from it. So let's see. Similar to the German name Isisag or Isisig. our ice vinegar. The name comes from the ice-like crystals that form slightly below room temperature. This is another name for it too. It's called anhydrous acetic acid. This word right here, what does that mean? Anhydrous. Close. So an means without. In this case, the hydrous refers to water. Without water. So
like on drink mixes, that's why if you buy a pre-made energy drink and the ingredients it's just caffeine, but if you get the powder, it's caffeine anhydrous. Is that why?
yes.
Been wondering what the difference was for a long time.
Oh, it's weird. I was looking up the etymology. I do this all the time whenever I see a word I don't understand. So it comes from Greek hudar, meaning water, and then an is of course Greek meaning without. So it becomes this, but then we Englishnize it, make it Germanic, by replacing the OS with OUS, and the UD hydrous. Weird. I was thinking that, like you, it comes from hydrogen, but no, it doesn't. It doesn't share the same root word as hydrogen. That is a weird coincidence that etymology come like that. But it just means without water. The sodium. So the thing we made, sodium acetate. The supersaturated solution I have is sodium acetate trihydrate. What this means, so sodium, Na, acetate is CH3COO. What this means is we put a dot and we put 3 H2Os. There is literally 3 water molecules bonded very slightly to these to the sodium acetate. You can buy and make sodium acetate anhydrous or anhydrate. But it's not going to stay anhydrate for long, as it will pull water and vapors from the air and actually turn it into trihydrate. Anyway, I want to make 1 molar acetate solution. One molar acetic acid, solution. Given that I have 100% vinegar. So what is molarity? What does this 1M mean? So molarity is defined as moles per liter. So to have 1 molar acetic acid means we have 1 mole of acetic acid. And this is 1 liter solution. And moles of solvent. Solute. Per 1 liter solution. Do y'all remember solute, solvent, and solution back from way beginning of the year? What is the solute? What's being dissolved? And the solvent is what's dissolving it. Usually the water. Water is the universal solvent. And the solution is the final mixture. Note the volume, the final volume is, we're doing the final volume. So that means we can't start, if we put 1 liter water and we dump into it 1 mole of acetic acid, would we have a 1 meter solution? So if we have 1 liter of water and we dump into it 1 mole, would this give us a 1 molar solution? What happens when you dump powder into something? The volume changes, right? So if I dump 1 mole of this into this, the volume is going to increase, and I'll no longer have a 1 molar solution. So, how would I achieve this? How can I make 1 molar acetic acid? If I were to go in the lab right now and tell y'all to bring me back a 1 molar solution, how would y'all do it?
What if you found out how much a mole weighed?
So what is the molar mass of acetic acid? So Na, not Na, this would be CH3, COO is acetate. I'm adding a hydrogen to it, so that's acetic acid. I've also calculated multiple times in your notes. What is the molar mass?
It was 60.05 and 96 grams per mole.
So 60.052 grams per mole is what you said. So that means there are 60 grams, I'm going to round this to 60 grams per mole. And y'all shouldn't round, I'm just doing this for brevity. That means there are 60 grams in 1 mole. So 60 grams is equal to 1 mole. So, again, 1 molar means I'm trying to make a solution that has 60 grams and has a total volume of 1 liter. So how would y'all do that? How can you get a 1 liter solution that has 60 grams of acetic acid in it?
Since the density is almost the same as water, maybe do milliliters and then subtract.
That's not very precise.
Well, for vinegar it was.
But you're right. It's not going to make too much difference. If you assume that they're the same density, and you did 60 milliliters of acetic acid, and then 940 milliliters of water. That's very, very, very close to a 1 molar solution. Don't do that though. There's a much simpler way. You are right. You can do very advanced calculations, but there is a very, very simple way. Y'all not see it? Let's say I have a cylinder with a marking of 1,000 milliliters on it, and I dump in 60 grams of acetic acid. What do I need to do now? I just fill it to the line with water.
That's what I was getting at, but with more complicated steps.
Yeah, we don't know if we're filling it up with 900 because this is in grams and this is in milliliters. Looking up, so doing it your way, if we made that error, acetic acid, density is 1.05. So 60 grams divided by 1.05. You should be adding 57 milliliters of vinegar, roughly. 57.142857 for, so 60 grams, it has a volume of 57. So you would have made something slightly stronger than, or slightly weak, slightly stronger than 1 molar. But this is still wrong. There's a very key thing of why you do not want to do this. Can anyone think of what that is? I'd be very surprised of why this would y'all would know this. So, what's the redox reaction? Alright, and what does it do? It produces energy and heat. I can't really say it's a redox. Here's something y'all might not know. What would happen if I take very strong concentrated acid and put a drop of water in it? It would dilute it. But what do acids do in the presence of water? They dissociate. It's hardly spelled. Meaning they break down in ions. Which means we're taking chemical bonds and we're temporarily breaking them. And what's a chemical bond but energy? So it does what? Produces heat. So if I pour water onto an acid, I don't know, it's going to boil the acid and you're going to have a giant acid fog coming into your face. You could kill everyone in the room. So, so we're definitely not going to put acetic acid at the bottom and pour water on top of it. What's another solution? It's very similar to this. I'm going to guesstimate initially. I know that 60 grams of vinegar is approximately 57 milliliters of water, milliliters of vinegar, right? That means if I fill this up to 800 milliliters water, and I dump vinegar in it, I won't be at 1,000 grams, right? Or 1,000 milliliters. So I then put 60 grams of acetic acid in here. And that will increase the volume to, it doesn't really matter, 857 milliliters. All I care about is the final volume. So I'll pour more water until it reaches 1,000 milliliters. So you do not want to pour your chemical straight in first. You want to have a good size of water. So if you know roughly the volume, you guesstimate the volume and you put less. Maybe you would start out with 500 milliliters of water, slowly pour in, and keyword slowly pour in your acid. And then once we make a super strong concentrate, then we start pouring in more water until it goes up. Does that make sense? Yes. Definitely do not pour water on an acid. It will immediately start boiling and splattering everywhere. I've learned that the wrong way, the hard way. Now, 1 liter, so you know your 2-liter bottles of Coke. 1 liter is half of that. That's too much to worry working with. I want to make 100 milliliter solution. How would I do it? So that's roughly 6 grams per 100 milliliter. That gives you a 1 molar solution. So I know that this is roughly going to have 6 milliliters. I'll double that to be safe, and thus use about at the most 80 milliliters of water. I then add in my 6 grams. That would bring it up to about 86 milliliters, and then I add more water until I get to 100 milliliters. And that'll give me a small 1 molar solution.